Alrighty, so we are going to continue on with some exponential equations. We're obviously, given relative time constraints and the fact that we're not going to cover as much material this year as we typically would, um, I'm going to just dabble a little bit further into exponential equations, not go nearly as far in as we would normally go, because I definitely want to get into the financial side of things. So we're going to explore a little bit, and then we're going to look at how exponential equations have applications into finance. Okay, so exponential equations. And then continuing into financial applications. Okay, so here we go. Hope everyone is doing well. It was an absolutely gorgeous day today, and it is meant to be a gorgeous day again tomorrow. Okay, so we have looked, we did exponential increase or exponential growth and exponential decay. And the general form I'm going to just write out is y equals, and I'm going to keep it really simple here. I'm just going to say a to the x, and I'm going to say plus b. And we know that this a value, the a, it dictates whether it's growth or decay, right? And we said that if a is greater than 1, we get growth. And what it looks like in general is it's always going to have a y-intercept of 1. And it goes like this and then just gets bigger really, really quickly. So that's exponential growth. And if a is between 0 and 1, we get decay. And it looks the exact same, but it's just being reflected. And so it also goes through at 1, but it grows on this side and then decays. Okay, so that's exponential growth and exponential decay. The b value, what the b value does, kind of like every other function that we've played with before, if there's a constant number hanging off the back of a function, that moves it up or down that many spaces, right? If it's plus b, it goes up b spaces. If it's minus b, it goes down b spaces. And that's, that's the constant value at the end of any function is going to have that exact impact. Okay, so, we'll explore, a couple of generalities, and then what I'm going to do is I'm going to show you, a bit of an intro into the financial applications of these exponential equations. Okay, so let's look at a couple of examples. So, for example, if we had y equals 5 to the exponent x plus 7. So this tells me we're going to have growth, right? We know that it's going to be growth. And so in the grand scheme, I know that this thing is going to look like this, right? And if we didn't have this 7 hanging off the back, if that wasn't there, all exponential equations always go through 1. And I used this word last time, but they're asymptotic. That means it gets closer and closer. The basic ones always get asymptotic to the x-axis, right? That's if the 7 wasn't there. So what that 7 is going to do is it's going to take and shift the important things up 7, okay? So if I were going to sketch this, here's what I would do. There's my x-axis, so I'll label that. There's my x-axis, this is my y-axis. Normally, so let's compare them. If I were going to graph y equals 5 to the exponent x, just that one, right? And I'm going to do that one in black, right? It would have a y-intercept of 1, and then it would get asymptotic over here. It's meant to be smooth, not bumpy like that. It's just hard for me to draw. And then it gets fat, big, fast, in a hurry, right? That's what y equals 5x looks like in black. Now I'm going to do y equals, maybe actually I'll do it in the right color. So let's do it in blue. I like blue. I think that's blue. So y equals 5 to the x plus 7. So I mean self-descriptive, it's in blue. So what's going to do is it's going to take those important points and it's going to move them up 7. So instead of the y-intercept being 1, the y-intercept is going to be up here and it's going to be at 8. And instead of it getting asymptotic to the x-axis, what I'm going to do is I'm going to draw in this line. So it used to get asymptotic down here to 0, right? Like this is an x value of 0 right here. So if we go up, it's going to be, this is now going to be at a y value of, a y value of 7, right? And so it gets asymptotic to the line. And so that line, it's not really there. It's just to kind of show you what's going on. But this gets asymptotic to 7, and it grows at the exact same rate. So this whole thing has just been shifted up 7. And that's all that B value does. It moves things up and down. In theory, if we were, in regular times, we would also explore y equals like m times a to the x plus b. And so the b's just the up and down. The a still dictates whether it's growth or decay. And the m value, it has a stretch factor to it. So just like if we had, remember back to if we did y equals, 2x squared plus 5x plus 7, that 2 is going to make the parabola thinner than normal, right? It would be a thinner parabola than normal. Well, what that 2 does is it actually is like an accordion that stretches it up and down. It does the same thing here. If I said y equals 4 times 2 to the x plus 7, what it would do is it would take the basic 2x graph and it would stretch it. But we're not going to worry about that right now. Okay, so in general, that's what this is going to do. And it works the same way whether it is growth or decay. So if I said y equals 1/3 to the x, let's say minus 2, right? So let's look at what the graph of that would look like. So let's do the basic one. So if we just had y equals 1/3 to the x, and I'm going to compare these graphs, 1/3 to the x, it doesn't have a b value hanging off the back. So because of that, it's going to have a y-intercept still at 1. But this number is less than 1 and greater than 0. So instead of it being growth, it's going to be decay. So it's going to go like this. Okay. That's pretty decent. There, that's that one. But if we take this one in blue or purple or whatever it is, um, what it's going to do is it's going to actually shift everything down by 2. No, I didn't carry my axis down. But, so I'm going to draw on another horizontal line. It's not really there. It's just going to help us, it used to get close to 0. Now it's going to get close to -2. And the y-intercept used to be at 1, but it's going to be shifted down 2. So now it's going to be down here at -1. But everything else about this graph is going to be the same. It's just going to take it and it's going to shift it down by 2. Right? So it would go like that. Right? So this b value only moves it up or down exactly that many squares. So this is sometimes called a that's not a v. It's sometimes called a vertical translation. Okay, so that's what the b value does. It moves it up or down that many squares. Okay, so as I've said, other years we'd spend another couple of days working on this, but I think that in this case, our time will be better served by exploring the stuff that's more relevant to you and that is more extensible for math in future years, next year, for instance. So we are going to look now at some financial applications. Now, I would ask, in class, I'm going to ask the question now, how many of you have a bank account? And I'm going to assume the vast majority of you have a bank account. Then the next question I would normally ask, and I'll ask it again, is what's the interest rate on your bank account? I bet most of you probably have no idea. And if I said to you, take a guess, what do you suppose your interest rate is? I'd like you to do that. Write it down somewhere or just think about it and hold it in your mind. What do you suppose the interest rate is on your bank account? And if you said anything more than like 2%, you're wrong. The reality is the vast majority of bank accounts anymore, even savings accounts, pay like 1/4 of 1%, or like 0.5%, or like student bank accounts sometimes pay up to 2%. My personal bank account pays me a grand total of 0% interest. And so it's like, wow, like times have changed. When I was a kid, when I was your age, back when dinosaurs roamed the earth, My bank account paid me between 7 and 8% interest, which is pretty substantial. So now I want you to think about, what is interest? You've probably heard interest rates and interest and stuff like that, but you probably don't really know what it is. Um, so, for those of you that have like no idea what interest is, when you put your money in a bank, in theory, if you put $100 away, in January and you went to get it out December 31st, there would be a little bit more than $100. The reality is these days it'd be like maybe 101 or at the upper end $102. That extra money is interest that the bank has paid you. Okay, so what interest is, basically, it is a fee paid for the privilege, I'm going to spell this wrong probably, of using someone else's money. And you think, well, what do you mean using someone else? Why would I get interest if someone? So here's what actually happens. We've got Hannah out there. Hannah's, been working. She saved up her money. She puts her money in the bank account. It doesn't just stay there. Like if you go and take money into a bank, it's not like it's sitting in a physical vault of theirs and it doesn't go anywhere. What happens is that Hannah goes and deposits her summer earnings of she made $2,500 this summer, puts it all in the bank to save because she's a responsible young lady. I need to do a kitchen reno, so I go into the bank and say, hey, I want to borrow some money, and the bank says, yeah, we can do that. What the bank actually does is it gives me Hannah's money. Um, and I use Hannah's money, but I pay a privilege to use Hannah's money. So maybe I pay the bank 5%. And so let's make the numbers really easy. I borrow $1,000 of Hannah's money for a year, and at 5%, that means I pay $50 in interest. Hannah puts that same $1,000 in the bank account. The bank might pay her 1%. So when Hannah puts in the thousand and she gets it out at the end of the year, she gets back $1,010. When I borrowed the money from the bank, I had to pay them back $1,050. Notice there's like a $40 difference there. That money is how the bank, it's one of the ways that banks make money. So it's interest. So a fee is paid for the privilege of using someone else's money. Well, when you put that money in the bank is paying you for the privilege of using your money because the bank is using your money for other things. When I borrow the bank's money, I'm paying for the privilege of using the bank's money until I give it back. So interest is a fee paid for the privilege of using someone else's money. And that's exactly what it is. Now, that interest rate is different depending on, what vessel you are borrowing it from. From a bank, the interest rates depending on what you're borrowing. So it's a really interesting, thing to think about. It depends on how risky things are. So the least risky investment that a bank is willing to give you money for is typically a house. Now, the reason that the banks consider houses pretty secure is that we've got Emma. Emma decides that she wants to buy a house, borrows $300,000 from the bank. That's an inordinate amount of money. And so, you would think that's super risky, but here's the deal. Emma goes and buys that house with the money she borrowed from the bank. Emma doesn't really own that house. The bank owns that house. So if Emma stops paying for her loan, the bank says, okay, we're going to take that house, we're going to sell it, and we're going to get all of our money back, right? So that's called collateral. The bank is pretty sure that they're going to be able to get, at the very least, most of their money, but in reality, probably all of their money back. So that's considered a low risk loan. And so because it's low risk, the banks don't have to charge you a lot of interest because they're not worried about it. Whereas a credit card, if I go out there with my credit card and I'm like, woohoo, I'm going to go and buy, an extra Nintendo Switch with Animal Crossing for the pandemic because that was useful for us. I go out and I do that. Who knows what's happened to my Switch? If I don't pay the bank back for, the money that was on my credit card, they're probably not going to come and find the Switch and then sell it, right? So credit cards are much, much riskier. Just like I could have just used it to go eat at Wabora every meal and racked up a huge amount of money. So interest is based on how risky it is perceived for them to give to you, which is, I'm overloading you with information like crazy. But suffice it to say, Interest is a fee that's paid for the privilege of using someone else's money. Now, interest, typically speaking, is compounded. So here's what I'm going to talk about: compound interest. And if you're wondering how this relates to the math that we're doing, that we've done with the exponential equations, you're going to see very soon. So compound interest means the interest you have already earned also earns interest, which I'm sure probably doesn't clarify things. It's most easily clarified with an example. So let's make this really, really easy. It's not going to be super realistic, but let's make it really easy just so we understand. So Haley deposits. So Haley deposits. We're going to make the numbers really easy. $10,000 into an account that pays, make the numbers easy again, 5% interest /A. That means per annum. So interest rates are almost always quoted in per annum, which is just a fancy way of saying per year. And then I'm going to say something that's, again, not going to mean much, but it's important to have it here: compounded annually. So that means it pays 5% per year and it's compounded annually. That means they only calculate your interest sort of once per year to make our lives easier. And what we're going to do is we're going to have it that Haley leaves her money, she invests, we'll make it simple again, for 2 years. Okay, so let's look at a timeline. So here's our timeline: 1 year, 2 years. And let's consider the money now. So this is 0 years. So at the very beginning, Haley drops 10 grand into a bank account. So at the beginning, she has $10,000. That $10,000 is going to sit there. And in a year, the 10,000 that we put there is still going to be there. And in 2 years, the 10,000 that we put there is still going to be there. But what she also gets is she gets 5% interest. So how do we calculate 5%? Well, hopefully you know that we're going to take that number and we can say 10,000 times 5% as a decimal. So anytime we want to convert to a decimal, we divide by 100. So you can just do 5 divided by 100, or you could have said 10,000 times 0.05, because that is 10, that's 5 divided by 1,000. So we dump that into our calculator. I'm going to grab a calculator because we're going to need it for this probably. I can do that one in my head, but other ones I might not be able to. Are you loading? Come on, there it is. Okay, so we're going to take and we're going to type that into our calculator, and we're going to say, all right, 10,000. That's not 10,000. 10,000 times 0.05, which is $500. So that means that Haley, in her first year, earns $500 interest, right? So at the end of year 1, if she took her money out after 1 year, she will have earned $10,500, okay? Which is good. But she is a scrupulous investor. She's going to leave it there for another year. So what's going to happen is that 10,000 that she's got in here, it's going to earn another $500 interest, right? So there's another $500 interest. This 500 is going to make it to the end. So there's another 500. But this 500 also earns interest to the tune of 5%. So her first year, she earned a total of $500 interest. The next year, she gets 500 off of the original 10,000, but she also earns interest on her last year's interest. So we need 5% of that number as well. So we're going to do 500 times 0.05. Okay. And what we're going to find out is that's like 25 bucks. Well, let's just confirm that. So we're going to take the 500, we're going to multiply it by 0.05, and it's going to be another $25. So her second year, she's going to earn an extra $25. So at the end of her 2 years, she will have earned 25011. So when she goes to take her money out at the end of 2 years, not having 10,000 in there anymore, she'll have $11,025. Now, there is a much quicker way of doing it than setting this all up. I just wanted to show what it meant to be compounding. So this compounding, what it does is the interest you've earned still earns interest. So fast way to add 5%, because this is really what we did. So if you remember back to grade 9, hopefully, how did we add tax to something? If you were in my class, we talked a lot about, I don't know, I'm going to say it, and for those of you who were in my class, I think there were a couple of you at least. If we want to calculate things, we can say the starting amount times some percentages is equal to the final amount. Okay, that's a formula that I used a lot with my grade 9s, and these percentages are important. Now, I want to add 5% to something. It means that I'm going to take the original 100% of the thing and I'm going to add 5%. So in total, we would have 105%, which as a decimal is 1.05. So if I wanted to do a quick calculation to go from here to here, I added 5%. I could have done 10,000 times 1.05. Right? So if I go and grab this calculator and I do 10,000, it doesn't like my pen to use like that, 10,000 times 1.05, what that does is it adds the 5% interest in right away. So that takes me to this number, 10,500. But then I'm going to take that number and I'm going to multiply it by 1.05 again, right? So if I come along here and I say, oh, I'm going to multiply that by 1.05 again, right? So I'm going to grab my calculator and I'm going to multiply that by 1.05 again. And we're going to get, there's the total, $11,025. Okay, $11,025. Now, that wasn't that bad doing that by hand for 2 years, but imagine that Haley, she's decided that she's going to set that money aside to a retirement. Haley's 16ish now. She's going to retire at the age of 60. So, that's going to be another 44 years away. I wouldn't really want to do this 44 times, although it would work. Certainly, I'm hopeful that you can recognize that what we actually have here is when I multiply two powers with the same base, what do I do with the exponents? I add them. There's an exponent of 1 there, an exponent of 1 there. So I could have simplified this to be 10,000 times 1.05 to the exponent 2. And let's just demonstrate, my daughter's watching something funny. Let's just demonstrate that that's the same thing. So times 1.05 to the exponent 2. And lo and behold, we get the same answer. So this takes us to our first significant formula for financial math. So this is going to be a compound interest formula. And this is one of those like circle it, highlight it, we're going to use this again kind of formulas. There's two variants for this formula, and I'll write them both out. We're going to say that A equals P bracket 1 plus I to the exponent n. There's one variant. And I'm going to define what each of these things are. So A is the final amount after interest is added. Okay, so A is the final amount after interest is added. Okay, no problem there. It's how much we end up with. It's the final amount. P stands for principal, which is a fancy way of saying the lump sum of money at the start of the problem. So it's the lump sum. So in the question we were just looking at, that's Haley's $10,000. It's how much money we put away at the beginning. And I say at the beginning, meaning like chronologically. Okay, so in time, when did this happen? Okay. Now, I is the next thing. And I is a bit more complicated than you might guess. I'm going to write it out, and it's going to sound complicated. It's not really, but for now, you're just going to have to keep up with me and write it down. So I is the interest rate per compounding period as a decimal. Okay, so it's the interest rate per compounding period as a decimal. So in the prior example that we had with Haley, she earned 5% interest compounded annually, which means once per year. And so to convert that as a decimal, anytime when you convert to a decimal, you divide by 100, right? So we took the 5, we divided by 100, and it was 0.05, okay? And then N is the total number of compounding periods. Okay, so that's one version of the formula. I'm not almost out of room. I'm pretty much out of room. I'm going to write the alternate version of the formula here. And so it is FV equals PV bracket 1 plus I to the exponent n. Now, look, symmetrically, they're very, very similar. We've got the 1 plus I to the n, 1 plus I to the n. The I and the n mean the exact same thing. So I'm going to put that here and that here. They are the exact same thing. Future value, final amount, it's the same thing. So final value is the same thing as A. And principal is the lump sum of money at the start of the problem. So present value means sort of the start of the problem as well. So here's why this one is sometimes a little bit more clear. Sometimes I might say, Kirkland needs to have $10,000 in 5 years. How much money does he need to put away now? That $10,000 is the future value because that's what he needs to end up with. And in that case, we'd be calculating the present value. Okay, so we're going to be really, really careful with how we do these things. So these two formulas are interchangeable, and I'm happy for you to use either one, whichever one squares away with you. This one seems to make more sense for most kids. This is the one that shows up in most textbooks, but a lot of textbooks will show this one as well. Okay, so I want to do some examples. So to do that, I'm just going to save this and get a new copy going on. I didn't think I'd need this much space. So I want to save that as a JPEG, and this is going to be MCF, and this is Financial Math Part 1. Alrighty, so Financial Math. That's lovely. All right, so File New. Awesome. So here we go. So we're going to continue on with more examples. So this is, financial math examples. So let's look at some example numbers to see what some of these things are. So imagine, so my daughter, so I invested, and again, we're going to make the numbers easy, but this is not far from the truth. I invested $1,000 when my daughter was born. To be a gift when she turns 18. I earn, let's do, 7% per annum. So that's 7% per year. And we're going to keep this one easy as well. Compounded annually. So that means once per year. How much is, question 1, how much is the investment worth on her 18th birthday? Birthday. It's not really looking good, whatever. That's the first question. And then the second question is, how much interest did we earn? Okay, so let us actually explore this. So for this one, I'm gonna use the A equals P bracket 1 plus I to the exponent. Now, if you think you can do it, by all means, pause this, give it a whirl. Anytime I'm gonna work with these, I'm gonna list out each of the variables that I'm responsible for. Now, the reason I'm listing, you might think, well, why are you listing A? We're always gonna solve for A. Well, we're not. Sometimes I'm gonna be solving for the P, and I know the A. But A is the final amount. Well, I don't know what that is yet, so I'm looking for that. So I'm gonna leave it blank. P is the principal or the starting amount. So it says I invested when my daughter was born. So that is the principal. So I'm gonna come down here and say, okay, the principal is $1,000. I is the interest per compounding period as a decimal. Okay, now here's the interest, 7%. So I'm gonna come down here and write 7%. And then I'm gonna say it's compounded annually. So that's per annum. So that's good. So I just need to convert that to a decimal. So I'm gonna divide it by 100, which is gonna equal 0.07. Okay, good. And then N is the total number of compounding periods. Well, it's compounded annually, okay? And we're gonna leave it there for 18 years. So the total number of compounding periods is 18. So I'm gonna fill all those in like that, and I'm gonna take these values and I'm gonna put them in my formula. A, I don't know, still just A. P, we said, is 1,000. So I'm gonna replace that with 1,000. Now, it's 1 plus I. I is 0.07. I'm going to write it as 1 plus 0.07 just for clarity. But really, normally on my own, I always just write it as 1.07 because I know that's what it's going to be because 1 plus 0.07 is 1.07. So you can write it like this or you can write it like this. This is what we're going to type in our calculator probably. So might as well just go there. N is the total number of compounding periods. It's 18. So I'm going to grab my calculator and I'm going to type this in. Okay, so I'm going to say 1,000 bracket 1 plus 0.07. You can even type that in if you have brackets, otherwise just 1.07, right? To the exponent 18. Okay, missed the 1. 18. Here we go. So $3,379.93. So $3,379. What was it? 93 cents. So first question was, how much is the investment worth on her 18th birthday? There it is right there. It's worth $3,300, almost $3,400. So that's the first question. Awesome. Second question is, how much interest did we earn? So interest is, again, it's the fee that's paid for the privilege of using your money. Now, I gave the bank $1,000 that the bank could work with and lend to other people or do whatever they wanted with for 18 years. So the bank has to pay a fee to use my money. Well, how much of a fee did they pay? Well, I put $1,000 away. So that $1,000 was always mine. So to calculate the interest, what we're going to do is we're going to subtract off the initial investment, and the stuff that's left over was how much interest we earned. So here we're going to say that interest is going to be the final amount minus the principal that I put there to begin with. So it's going to be 3379.93 minus that $1,000 that I put away to begin with, which is $2,379.93. So the bank paid me for the privilege of using my money for 18 years, almost $2,400, which seems like a lot. And it is. It's a lot of money. Okay, it's amazing, and we're going to explore this, how big a difference the interest rate will make. We're going to get to that. Okay, so let's look at a second question. So let's ramp it up a little bit. So Bree invested $2,000 at, we're going to go with some easy numbers here, 8% per annum. Okay, so that's 8% per year. Here's where it's going to get interesting. Compounded, and I'm going to do this one as quarterly, we'll do it for 10 years. Same two questions. What is the final investment worth? So it's the final amount. And the other question is, how much interest did we earn? So A equals P bracket 1 plus I to the exponent n. List out the variables, A, P, I, and n. A is what we're looking for. It's the final amount. Principal, it's the lump sum at the beginning. So she invested $2,000. So there's my principal, 2,000. This is where it gets a little bit more interesting. Now, interest is always quoted per year. Okay, so over the period of 1 year, so this is January and this is December, okay, for 12 months, over that entire period, we earn 8%. But here it says we're going to compound quarterly. So we're going to separate this into blocks, into 4 blocks. 1, 2, 3, 4. In total, for the whole year, we get 8%. For each of these quarters, 8 divided by 4 is 2%. Right? So each one of these quarters earns 2%. So I said in the definition, if you go back, that I is the interest per compounding period as a decimal. So in this case, it is 2% as a decimal. Here's what we're always going to do. We're going to take the quoted interest rate, 8%. We're going to divide by the number of compounding periods in the year. Quarterly means 4. So you're going to take the 8, divide it by 4, and that's going to be 2%. But I want 2% to be a decimal, so I'm going to divide that by 100. And so when I divide that by 100, it's going to be 0.02. So that is the interest per compounding period, 0.02. Next, N represents the total number of compounding periods. Total number over the entire life of the loan, the investment, the whatever it is. So I get 4 quarters per year, and I have 10 years. So hopefully you can do that math in your head. That's going to be 40 compounding periods. So the easy way we can always do it is it's going to be the number of years times the number of compounding periods per year, 4, which is 40. Now, I want to point out to you, the number that we divide by here is always the same number that we multiply by here, always, okay? Always going to be the same, okay? So that's lovely. What we're going to do now is calculate the answers to these things. So we're going to take this formula, we're going to substitute these things in. So A is equal to, principal is 2,000. It's going to be 1 plus 0.02, so just 1.02 to the exponent 40. Right? So what I'm going to do then, go grab my calculator. So we're going to have 2,000 bracket 1.02 to the exponent 40. And I'm going to find out $4,416.08. So $4,416.08. Now I want to show, I know there are some of you that have like an older one-line calculator. The way you would type this in with a one-line calculator is we could just type it in as 2,000 times 1.02, and then you'd use your exponent button, probably y to the x or x to the y of 40. Don't need to do with the brackets like I was doing, but there it is, same answer. Okay, so that means at the end of the 10-year period, her $2,000 investment is now worth $4,416.08. Right? That's what the final investment is worth. Now, that's the final amount right there. Now I want to know how much interest. Well, the interest is the difference between how much is there at the end and how much I put there to begin with. So the interest in this case is going to be $4,416.08 minus that $2,000, which is $2,416.08 interest. And there it is. Okay. So that's a really, really, really basic start on compound interest. Okay. We are going to explore this much more thoroughly soon. But for now, I think that's probably good. Have a lovely day.